In the last few videos, we learned how to calculate the force that results from an uneven pressure distribution on a planar or straight surface, as well as the line of action of that force. In this video, we're going to add a little bit of complexity and look at the distribution of pressure, the resulting force, and the line of action on curved surface. So we're going to look at a situation that looks something like this, where we have some arbitrary curved surface between point A and point B submerged in a fluid, in this case water. And the first thing we need to notice is that I've drawn the pressure distribution along that curve. As we move from A to B, the pressure magnitude of that force gets smaller because we're moving into shallower water, but also the direction of that force changes because the pressure always acts normal to that curve. In order to calculate that resulting force, what we're going to do is look at that differential tile, the same differential tile we looked at for the planar case. So let's draw that out. So we have this differential tile, something like this. It has some width b into and out of the board and some length ds along the curve itself, and it has some differential area dA. Okay, so that's our little tile, and we're going to look at that in section. So we have some curve like this, and that's ds, and it has some differential force dF acting upon it like that. Okay, so that's our little piece there, and we can define that dF. We did that in the previous example. So dF is equal to the pressure times the differential area, which is equal to the specific weight of the fluid times the depth of that differential piece times the width b times the length ds. So that's our expression for the differential force on our little tile. And at this point, we can actually do a line integral from A to B and calculate what that resulting force would be. However, in practice, that is fairly difficult. It involves a fair amount of complex trigonometry because the orientation of that curved surface is always changing. And so instead, what we want to do is decompose this system into its two components, a horizontal and vertical component. So let me draw that out, and then we'll look at the horizontal and vertical components respectively. So first thing we want to do is take the force, and we're going to separate it into a horizontal component, dFH, and some vertical component, dFV, and they're going to be separate, and then we're going to have some angle here, alpha. Okay, we'll do the same thing for the surface itself. So we're going to have some horizontal component, dx, and some vertical component, dh, and then some angle, the same angle alpha here. Okay, so that's the situation we have where we're breaking this into a horizontal and vertical component, both the force and the surface itself. Okay. So now let's take a look at the horizontal. So first, look at the horizontal. Okay, so we have dFH. We can define that again. We already did that, so we're going to write that out. dFH is equal to gamma, the depth of that differential tile, times the width, times the change dH. Okay, so now we have dH is the vertical component, the width, so we have that cross-sectional area, and then the horizontal force, the pressure, gamma times the depth. Okay, and we can make a couple substitutions there to end up with is also go to gamma times h times the width times the differential length of the surface times the sine of alpha. Right? So that's just simple trigonometry. And if we look at this component here, this part of the equation, that is just the vertical projection of the surface itself. So we can give that the definition AV where AV is the vertical projection area. So if we took a light and backlit our surface, the vertical projection of the area would be the shadow that it leaves in the vertical. And so we can rewrite this now as DFH is equal to gamma times H times the differential area, vertical area of the vertical projection. Okay? And at this point we can integrate that, so we can integrate it. The gamma comes out, and we get H times DAV. And if you recall from our previous lecture, this is the first moment of the area, right? And so we know how to calculate that. That's the centroid. So we end up with F of H is equal to gamma H at the depth of the centroid of the vertical projection times the area of the vertical projection. So it's pretty straightforward. And we can write that another way. It's the pressure at the centroid of the vertical projection times the area of the vertical projection. Okay? And then similarly, we can look at the line of action for line of action. It's going to be the same thing we went through with the planar surface, where we're going to end up calculating the second moment of inertia of the vertical component, and we end up with H sub r minus H at the centroid of the vertical projection is going to be equal to the second moment of the vertical projection, centroid of the vertical projection, times H centroid of the vertical projection at the centroid of the vertical projection times the area of the vertical projection. So it ends up being exactly the same as for our planar case. We're actually calculating the pressure distribution on a plate that's in that vertical projection sense. Pretty straightforward. Okay, so now let's take a look at the vertical component. Okay, so in the vertical component, we can write the same thing out. So we can look at our differential force in the vertical direction. It's going to be equal to gamma H D, H B ds cosine of alpha. So I've just done the same thing and substitute the sine of alpha for the cosine of alpha to get the vertical component instead of the horizontal. And if we look at the fluid volume above the vertical tile there, so if we look at the differential volume of the fluid above our surface, that's going to be equal to HB ds cosine of alpha. Okay, and you see pretty quickly there that this expression and this expression are the same, so we can substitute that in, and we get df of v is going to be equal to gamma times d times the differential volume. We can integrate that. Gamma comes out, we get integral of the differential volume, which is equal to gamma times the volume. So the resulting pressure force due in the vertical direction is simply the weight of the fluid above the surface. And it's relatively easy to calculate. Instead of having to go through all the trigonometry in the line integral, we can simply, for the horizontal direction, we calculate the resulting force on the vertical projection of that surface. And for the vertical component, we calculate the weight of the fluid above that surface. Okay? Finally, for the line of action, for line of action, in the vertical, I'm not going to go through the full derivation because it's actually pretty straightforward. The centroid of the fluid volume above the surface. So basically, for the centroid of the fluid volume above the surface is the line of action for the vertical component. And that's how you do it. You can break it out into the horizontal component and the vertical component. Again, we look at the vertical projection and calculate the resulting force on that vertical projection for the horizontal component. And for the vertical component, we actually just calculate the weight of fluid above the surface between the 2 points in the horizontal. Okay, in the next video, we'll look at a quick example.